Very good. Now the experiment we're going to carry out allows us to measure K max. And from that measurement, we can deduce, for example, what H is. So our goal in the experiment is to measure K max. And we're going to do that with the apparatus shown here. Look carefully. First, we have a phototube which contains the cathode, the photocathode, in a glass envelope. It also contains an anode. So when electrons are excited from the photocathode, if they reach the anode, well, that'll correspond to an electric current flowing from cathode to anode, or electrons, cathode to anode. And then these electrons will run around the circuit so they're available at the cathode to be re-excited. Thus, we can measure the presence of a photocurrent by inserting an ammeter into the experiment. And when we shine light onto the photocathode, we should measure a current in the experiment. Okay? Finally, we're going to add a voltage bias in this experiment. That is, we'll introduce the battery that's shown here. One second. So what's the point of the battery? Well, with the battery, we can do the following. Suppose that we apply the voltage in this sense so that the cathode is positively charged relative to the anode. Then we can see what will happen. The anode will be negatively charged, which means that it will repel electrons. And if we make this voltage large enough, the anode will repel all electrons that leave the photocathode, so that no electrons will be able to travel from cathode to anode because the repulsive force will be too strong. Here, we can make another energy diagram that illustrates what we're talking about. So in this diagram, the vertical axis is also energy. So we have the energy near the cathode and the energy near the anode. And the energy difference between them will just be the electrostatic energy, E, times the voltage difference. And you can see that if E times the voltage difference were to be greater than the kinetic energy that an electron has, the electron would not be able to climb this hill to go from the cathode to the anode. Okay? So we can imagine if we set this up and turn on the light with V set to 0, we'll see a photocurrent. But as we increase V, the photocurrent will become less and less because some of the electrons will not have enough kinetic energy to cross from cathode to anode. And finally, when the potential energy barrier is as large as the maximum kinetic energy, then no electrons will have enough energy to cross from cathode to anode. The critical point where the current goes to 0 should be the following. It's the point where the height of the potential energy hill is equal to K max. We call that special voltage the stopping voltage. So I'll write it here. Okay? But we know already from energy conservation that K max is just HF minus the work function. And so that means that there's a relationship between the stopping voltage and the frequency in the work function. There we are. Okay. And so this is the relationship that we want to explore in our experiment. And let's see why. Look at this relationship. It relates things that we can easily measure. The frequency and the stopping voltage. And the relationship is a linear relationship. And it contains this very interesting constant, Planck's constant, okay? So according to this relationship, if I were to make a graph of the stopping voltage for different frequencies of light, what we should find is that they're linearly related. That is, the data, if we do the measurement for different light frequencies, different colors of light, the data should fall along a straight line. And you can see that the slope of the line will just be h over e, okay? While the intercept of the line will be the work function over e. So according to Einstein's theory, we can do this experiment and we should find that the stopping voltage is linearly related to the light frequency. It's hard to explain that relationship in any other way than with Einstein's theory. So that's strong confirmation of the theory. But there's more. If we do the experiment and it works, then we can use the experiment to determine a value for Planck's constant, one of the fundamental constants of nature. Okay? And that's a second goal of our experiment. What's more, once we fit the data and find both the slope and the intercept, we can use the intercept to find the work function of the metal. Now, this isn't a fundamental constant of anything. It's just a property of the particular metal that was used to make the photocathode. Okay? But I will say that these days, when people do experiments like the photoelectric effect, which they do, it's called photoelectron spectroscopy, what they're actually doing is using this physics to map out the energy of all those electron states within the conduction band. So they're actually interested in finding something like the work function of novel materials. So the photoelectric effect is alive and well in photoelectron spectroscopy. Okay, I think we can stop there.